In this section, we'll introduce a couple of rules for taking derivatives of polynomials and exponential functions quickly. So if we have a function y is equal to f of x, we had been using this limit definition to find its derivative. And here, this was the notation we used to represent the derivative of the function. There are a couple of other notations, so I'll introduce those now. You can also write dy dx when you're talking about the derivative of your function y. Here, this derivative is representing a slope, and this notation kind of indicates that. You can also write d dx of the function f of x, which means take the derivative of f of x. In example 1, I want to use this limit definition to prove these two rules, that the derivative of a constant is equal to 0, and if you take the derivative of just x, you will get 1. Starting with the derivative of a constant equaling 0, I'd like to justify this by looking at a graph of a constant function, which will be something like this blue line here. So the blue function is f of x is equal to c, and it's a horizontal line. Horizontal lines have slope 0, and that's why the derivative of this function should be 0. But proving it using the limit definition will look like this. If we're taking the derivative of a constant, that is the limit as h goes to 0 of, my function is f of x, so first it'll be f of x plus h, but no matter what you put in place of this x, including x plus h, the answer is always c, and that's the first thing that would go here. There is no x over here, so you can't substitute an x plus h. We then subtract the function itself, which is also subtracting c, and we're dividing by h. Why does this limit equal 0? It's because when you simplify, we get the limit as h goes to 0 of 0 over h, which is really just the limit as h goes to 0 of 0, and that should equal 0. So here, we prove this fact using the limit definition over here. We never have to use this again. We can just keep this as a fact. If we see a constant, its derivative must be 0. Likewise, here, what about the derivative of x is equal to 1? So here, this is the function f of x is equal to x. I'll label it down here. The slope of this line is 1, so that should be the derivative, but let's check that using this limit definition. If we take the derivative of x, that's the limit as h goes to 0 of, first, we put x plus h in place of x. So here, you can actually plug in your x plus h. And then you subtract off the function itself, which is subtracting x. And this whole thing is divided by h. If we simplify the numerator, the x's actually cancel, and we just have h left over, and we're still dividing by h. When we cancel the h's, we get 1. And the limit of 1 is 1, which proves this rule here. So if we see something just like x, we know its derivative should just be 1. So we have these as rules now. We never have to do these types of computations again. I'd now like to introduce a very important rule when it comes to taking derivatives. This is much more general than the two previous ones we did. But what happens if you take the derivative of x to a power n, where n is any number? You could prove this using the limit definition. Take the limit as h goes to 0 of, and you'd have x plus h to the nth power minus x to the nth power over h. And if you assume that n is a positive integer, you can expand this out, you can cancel the x to the n and simplify it. It's a lengthy proof, but what you get at the end, after taking the limit as h goes to 0, is the following. It's n times x to the n minus 1. So I won't introduce the proof here, but you can prove this fact for positive integers n. What we're going to do is just simply apply this, and we're going to assume that it works for any number that we want, n. Let's try this in example 2, where the only directions are to differentiate, meaning take the derivatives of these expressions. Let's start with this one, the derivative of x squared. We don't have to use the limit definition anymore. We can just note that here, well, n is equal to 2. So the derivative is, okay, you take the 2 and you bring it down front, so that'll be 2. You copy down the x, and then you subtract 1 from the exponent. And it simplifies to just 2x, which is the answer. So no more limit definition. We can just use this fact to quickly go from here to here. We can do the same thing for the derivative of x cubed. What about this? Well, here, n is equal to 3, but it works the same way. You bring the 3 down front, you copy down the x, and you subtract 1 from the exponent, which gives you an answer of 3x squared. So we're getting the answer very quickly. With the limit definition, it's a long computation. Well, what about here in this next one? This is the square root of x, and that's the same thing as x to the 1/2 power. So here n is a half. Now, this rule works for any number, so the answer would be the following. You take the 1/2 and you bring it down front, just like any other number. You copy down the x, and then you subtract 1 from the exponent. So that's going to be 1/2 x to the, 1 minus a half, that's 1 minus 2/2, that's negative 1/2. This is a completely acceptable answer. However, you can write this with a positive exponent if you move it into the denominator. And the second that it's x to the 1/2, you can also replace it with the root symbol. So any of these three are a fine way to write your answer. This one is simplified without using any negative exponents. So, just to recap here, this, when I did 1/2 minus 1, the way I'm thinking about it really is, do 1/2 minus 2/2. It's easy to write 1 as a useful fraction here. So when you subtract the exponents, you have negative 1 left over. So that's what I did here. Okay, last part. Well, these were pretty simple, but what about the derivative of this thing? What we can do is just differentiate each part of this using the rules that we have. Let's see how this will work. Okay, starting with this 5x to the 4th, well, we'll bring the 4 down front, and there's a 5 here. What we do is we multiply those two numbers together to give us 20x cubed. We then subtract off, now I have 3x squared. I bring the 2 down front, but there's already 3 here, so I'll multiply those two things together, and that gives us 6x to the 1st. I now have 2x. Well, I know the derivative of x from the previous slide is 1, and if I multiply that by 2, I get 2. The last thing is we have minus the derivative of a constant, which is 1, and we saw last time that the derivative of a constant is 0. So we very quickly get to our answer of 20x cubed minus 6x plus 2, and that thing is the final answer. So we're basically applying this rule with the added idea of if there's a number here, you can take the 4 and multiply it to the 5, and then subtract 1 from the exponent, and we work our way down this expression. Now, technically, in this process, we used the following facts. That if you take the derivative of a sum or difference of two functions, then you can go through and take the derivative of each part individually, adding and subtracting as you go. So we're just going to, again, use this fact to take the derivatives of sums or differences, but you can actually also prove this using the limit definition if you want to. So, this technically is a rule that I used. Along with this one, if you take the derivative of a constant times a function, well, that's the same thing as taking that constant and multiplying it by the derivative of the function. So this rule we used when we just went through term by term and took the derivative of each part. And this rule we used by bringing the 4 down front, we multiplied the 4 to the 5 together, so the constant gets multiplied by the derivative of the function. All right, so that's it. Let's try this out in a couple of other examples. All right, let's try these. Differentiate g of t and h of w. So we're still going to be using the rule on the previous slide, which is we're taking the derivative of some variable to a power, which gives us n times x to the n minus 1. But sometimes your function will not be written so it exactly looks like this. If that's the case, that means you have to simplify your expression so it does look like this. Like here I have a 1 over t, and here I have a 7 over the cube root of t. Those don't look like this. And not just because the variable is different, but here I have a fraction. Here I have a root symbol. And the first one actually is set up perfectly to use this, but these two aren't. So as a first step, I'm not going to take the derivative, but I'm going to rewrite the function. This is for t to the negative 3/8 plus, okay, now we have a fraction. How can I write this so it looks more like this? And the way we can do this is by saying t to the negative 1. So that is, if you have something in the denominator and you want to move it to the numerator, you can make the exponent on it negative. Now here, 7 over the cube root of t, so that is 7 over t to the 1/3. That means if I want to write it so it's not a fraction, that's plus 7t to the negative 1/3. This is now expressed in a way where I can apply this rule to take the derivative. The derivative is g prime of t. Okay, I bring the 3/8 down front and I multiply it to the 4. That's negative, okay, 3 divided by 8 is a half, so we get negative 3 halves. Then we have t to the, okay, I'm subtracting 1, which means I'm subtracting 8/8. That's negative 11/8. For the next piece, I bring down the negative 1. I'll just put negative t, and if I subtract 1 from the exponent, I get negative 2. For the next piece, if I bring the negative 1/3 down front and multiply it to 7, that's negative 7/3 times t to the, okay, negative 1/3 minus 3/3 is negative 4/3. And this is the answer. If you want to express it with no negative exponents, you could say this is negative 3 over 2t to the positive 11/8 minus 1 over t to the positive 2, and then minus 7 over 3t to the positive 4/3. So it's very simple to take negative exponents and make them positive in a denominator, or if you see something in a denominator, move it to a numerator by making its exponent negative. Now, what about the derivative of this? I put this one in here because I'd like to show you first how not to take the derivative. It's very tempting to say, to take the derivative of this function, you can just take the derivative of the top and the bottom, which would give you, well, we have 4w to the 9th, which is 36w to the 8th, minus 16 times 4, that's 64w cubed. And we know from the previous slide that if you take the derivative of the square root of something, that's plus 1/2 w to the negative 1/2. And then if you take the derivative of the denominator, you get 4w cubed. And this is wrong. You cannot do this. We don't have a rule that says if you have a fraction, you can just take the derivative of the top and the bottom. So what we have to do is somehow change this so we can write it as a sum or difference of functions. Here's how you can do that. What you can do is split this into 3 fractions, like this. And I'll put w to the 1/2 first, like that. Now we can simplify. Well, if you have 4w to the 9th over w to the 4th, that's 4w to the 5th. And I got that by subtracting these two exponents. Here they completely cancel, leaving you with just minus 16. And then for this last part, again, we have w's with exponents, meaning we can subtract those exponents. 1/2 minus 4 is, that's 1/2 minus 8 halves. That's negative 7 halves. We haven't taken a derivative yet, but it's now written in a way where we can take the derivative. The derivative is 20w to the 4th minus, the derivative of 16 is a constant, so it's 0. And then it's going to be minus, now I bring the negative 7 halves down front, so the minus and a minus becomes a positive. We get w to the, and if you subtract 1 from the exponent, 7 halves minus 2 halves is minus 9 halves. The derivative I'll leave as 20w to the 4th plus, I'll write it with a positive exponent, 7 over 2w to the positive 9 halves. So in the previous slides, we took derivatives of polynomials, or things that reduced to polynomials. But what about exponential functions like a to the x, like 2 to the x, which is graphed down here? The rule is as follows. It is a to the x times the natural log of a. And just a quick point of confusion, it's very tempting to try to use the previous rule on this, where you'd bring down the x, copy down the a, and subtract 1 from the exponent. But this is wrong. And the reason is our previous rule had the variable in the base and the number in the exponent. And that is the opposite of what we have here. So this is the rule that we have to use. This is not a rule that we can use. Let's see what that looks like down here. The graph of 2 to the x is given below. That's this thing. I said let's first consider what the derivative looks like. And then can we use this rule to find the derivative? If you try sketching the derivative function, and I'll just mark this as f of x is equal to 2 to the x. Is the derivative ever 0? And the answer is no. The reason for this is there's no time when it changes from like increasing to decreasing or decreasing to increasing. In fact, this thing is always increasing. It's always moving up. It's not very steep here, but it's still a positive slope. So that being said, is the derivative ever negative? And again, no. It is only positive. And that's because f is increasing. It starts out with a very small slope, and then the slopes become bigger and bigger and bigger. If you try to graph the derivative of this function, you get something that looks like, well, a lot like the function that you start with, an exponential function. So this is the derivative. That's what this rule says. It says if you take the derivative of an exponential function, you almost get the same thing back. This and this should be really similar. It's just scaled by some number, and that number is the natural log of a. So according to this rule, the derivative of 2 to the x is simply 2 to the x multiplied by the natural log of 2. If you type the natural log of 2 into a calculator, it's roughly 0.7. And that makes sense with the graph that we have. The derivative, it's the same function, but you're multiplying every y value by 0.7, which drops it down a little bit. So it's the same graph, it's just a little bit lower. More formally, if you want to see why this is true, you can look at the limit definition of the derivative. That is, if you take the derivative of 2 to the x, or any number to the x, that's the limit, as h goes to 0 of 2 to the x plus h minus 2 to the x all over h. You can simplify this. This is the limit as h goes to 0 of, well, 2 to the x plus h is 2 to the x times 2 to the h. And written this way, you can factor out 2 to the x from the numerator. So we have this. We can split this up into two separate pieces. This is the limit as h goes to 0 of 2 to the x times 2 to the h minus 1 over h. Well, the 2 to the x will not depend on h going to 0, so this thing stays. And then this part over here, this thing, is just it's a number. So this thing is equal to 2 to the x times some number. Because as you let h go to 0, nothing happens to this, but this should equal some value. And what's that number? That number exactly in this case is the natural log of 2. In general, for any exponential function, it's the natural log of that base. In example 5, we have the function e to the x minus x cubed. I'd like to find the first and second derivative of this. And then afterwards, I'd like to find the equation of the tangent line to f at x is equal to 0. So to start with, what is f prime of x? Okay, it's the derivative of e to the x minus x cubed. And just as a reminder, the number e, it's a constant. It's roughly 2.71828, and it goes on forever. According to the rule on the previous slide, the derivative of e to the x is e to the x times the natural log of e, minus the derivative of x cubed is 3x squared. What is the natural log of e? The natural log of e is actually 1. What does this mean? When you take the derivative of e to the x, it actually is just e to the x. And this is a very important rule. We'll often use the function e to the x. And when you take its derivative, it's equal to itself. There's no need to write this any time. If you ever see e to the x alone and you're taking its derivative, you can simply say, oh, well, the derivative is e to the x, then we have minus 3x squared. Now, what about the second derivative? What does that mean? The second derivative just means you're taking the derivative of the original function twice. Or, if you have the first derivative, take the derivative of this thing. So that means we're first taking the derivative of e to the x, which, as we said, it's just e to the x. And then we have minus the derivative of 3x squared, which I bring the 2 down front, and I get 6. Copy down the x, and subtract 1 from the exponent. You can do this process forever. You can have a third derivative, which would be e to the x minus 6. You could have a fourth derivative. Once you get to a derivative higher than 3, you can put the number of marks in parentheses like this to indicate you're talking about a fourth derivative, and that's just going to be e to the x. And in fact, any derivative you take after 4 will always be e to the x, and it never goes away. But for this problem, I really just wanted the first and second derivative. Okay, now we have this. What is the equation of the tangent line to the original function when x is equal to 0? And just a reminder of that process, you need a slope and you need a point, x1, y1. The slope is the derivative of the function at the value we care about, which is 0. And x1 in this case is also equal to 0. Well, we have a formula for the derivative at 0 is e to the 0 minus 3 times 0 squared. So that's e to the 0 minus 3 times 0 squared. And that's just equal to 1. All right, now what about y1? That's the value of the function at x1, which is f of 0. So that's going to this thing and putting 0 into the x's. That's e to the 0 minus 0 cubed, and y1 is also 1. If you put this information into the formula for the equation of a line, this thing, that's y minus y1, which is 1, is equal to m, which is 1, times x minus x1, which is 0. You can simplify this. This is y minus 1 is equal to, well, I don't need this minus 0 or this 1, and I can just put x. And if I add 1 to both sides, I get that y is equal to x plus 1, and that is the equation of the tangent line to the original function at x is equal to 0.